Namaste students, and a very warm welcome to all of you. Today, we are going to learn a very important topic from Unit 6, electromagnetic induction. We will learn Faraday's law of induction, and I promise we will learn it so simply that you will never forget it, and you will score full marks in your exams. Chalo, let's begin.
Okay, to get started, let's dive right in with a question that will really make you think. So first, I want you to consider this simple mystery that puzzled scientists for a very long time. We all know, right, that to get a current, you need a battery. You need something to push the charges. But what if I told you we can get a current, we can make electricity flow with just a magnet and a loop of wire? No battery connected at all. How on earth is that possible? And here's where it gets even more surprising. You might think, okay, sir, maybe we have to move the magnet. But what if I told you that even if the magnet and the coil are both perfectly still, at rest, we can still generate a current? This is the magic we are going to understand today. So let's move on and see how this all builds up. The fundamental idea behind all this, it's actually very simple. Now, what's really interesting about this slide is that it captures the whole secret in one single line. The key word here, the most important word, is change. It's not the magnetic field itself that creates the current. A magnet can sit next to a wire all day long and absolutely nothing will happen. What matters is the change in the magnetic environment. That change is the real hero. To make this idea really solid in your mind, think of it like this. Imagine that these magnetic field lines are like invisible ropes passing through our wire loop. Now, if these ropes are just sitting there, steady, nothing happens. But the moment you start to disturb them, you squeeze them, or you stretch them, or you cut them, they give a little tug on the charges inside the wire, and that's what creates the current. So it's the disturbance of these ropes, the change, that causes the effect. Okay, now for your exams, this part is very important. You must write the formal law and the formula perfectly. So let's look at the exact wording from your NCERT book. And this is the man himself, Michael Faraday, a brilliant scientist who discovered this relationship after doing so many careful experiments. He's the one who figured out exactly how to describe this amazing effect.
बच्चों, इस point को note कर लो. This is the exact statement you must write to get full marks for the law. All it's saying is that the voltage you get, the EMF, depends on how fast the magnetic flux is changing. A slow change gives you a small voltage. A very fast change gives you a big voltage.
Now, mathematically, that whole statement is written just like this. I know, it might look a little complex at first, but trust me, it's very simple. Let's break it down together. Each part here has a very simple meaning. First, this symbol, epsilon, is the induced EMF. Basically, it's the voltage measured in volts. N is just the number of turns in your coil. Simple. Then you have this phi with a B, which is the magnetic flux. And finally, this d by dt part. Don't let it scare you. It's just a mathematical way of saying rate of change with time. That's all.
Okay, so we keep talking about this magnetic flux, but what is it really? Let's quickly understand this concept.
देखो, it's actually just a way to count how many magnetic field lines are passing through your coil. That's it. And it depends on just three things. B, the strength of the magnetic field. A, the area of your loop. And cos theta, which depends on the angle between the field and the area.
Right, now let's apply this with a very simple example from your textbook to see how it works. So, step 1 is the setup. We have a square loop in a magnetic field. Step 2, here's the change. The magnetic field is decreased to 0. And step 3, this change happens in 0.70 seconds. So the question, step 4, is what is the induced EMF and current? So all we have to do is calculate the change in flux and divide it by the time. By plugging the values into our formula, we find the induced EMF. The calculation is very straightforward, and we get an answer of 1.0 millivolt. And once we have the voltage, the EMF, finding the current is super easy, right? We just use our old friend Ohm's law. Current I is just the EMF, epsilon, divided by the resistance R. And that gives us a current of 2.0 milliamps. See? It's that simple. Nothing to be afraid of. Okay, this next part is extremely important for your exams. To avoid losing marks, we have to talk about some very common misconceptions. I call them silent killers because they can trap you. Let's make sure you don't fall for them. So many students make this first mistake. They think, oh, there's a magnetic field, so there must be a current. No, that is the wrong idea. A strong, steady magnetic field does absolutely nothing. The correct idea is that a changing magnetic flux is necessary. Please just burn this line into your mind. Say it with me. No change in flux, no current in the circuit. This one sentence, I promise you, will save you from so many wrong answers. All right, so I think we have understood the complete concept now. Let's do a quick summary and then see where this amazing idea takes us next. These are the 3 golden points of Faraday's law that you must remember for your lifetime. First, an EMF is induced only when the magnetic flux changes. Second, the size of that EMF is equal to how fast that flux changes. And third, the amount of flux itself depends on the field, the area, and the angle. You know, this law revealed something incredible, a deep connection in nature. Before Faraday, we thought only charges, like electrons, could create electric fields. But now we know a changing magnetic field can also create an electric field. And it's this new electric field that actually pushes the charges in the wire to create the current. And this leaves us with a final fascinating question. You know, nature loves symmetry. So if a changing magnetic field creates an electric field, what do you think a changing electric field creates? Think about it. We will find the answer in the next chapter on electromagnetic waves.